Okay folks, this is a refraction, part of the particles and waves unit in the higher physics course. Firstly a wee intro though. Now you did do refraction at National 5, where we spoke about refraction as the slowing down of light when it goes from air into glass, and when the light enters the glass at an angle it bends towards the normal and so on, but we will come to that in due time. Firstly though, here's a wee intro. Look at this wee picture. There's some people running down the beach. If a crowd of people run down the beach into the sea, the water is harder to move through, so the people that enter the water, they will slow down and bunch up. They will get closer together. The number of people, however, will stay the same. Now this is similar to the idea behind refraction of light. When light enters a more dense substance, a more dense medium we would call it, for example glass, then the light waves slow down and bunch up. So refraction is the slowing down of light as it passes from a less dense to a more dense optical medium. Now an optical medium is just a substance that's transparent that lets light pass through it. So for example, if we go from air to glass, the light slows down. Now the absolute refractive index of a material is the ratio of the speed of light in a vacuum to the speed of light in the material. And because it's a ratio, refractive index has got no units. Probably a little example would make things a wee bit easier, but there's the relationship. N is the symbol for refractive index, and V1 is the speed of light in a vacuum, and V2 is the speed of light in whatever material it's passing into. The more dense medium, the more optically dense transparent substance. Here's my wee example then. What happens if light goes from a vacuum into perspex? Well, the speed of light in a vacuum is 3 times 10 to the 8. The speed of light in perspex is only 2 times 10 to the 8. So calculate the absolute refractive index of perspex. It would be 3 times 10 to the 8 over 2 times 10 to the 8 is 1.5. No units. That number 1.5 is just telling us that the speed of light is 1.5 times greater in a vacuum than it would be in the substance. Now, you don't get light travelling from a vacuum into substances here on Earth because we've got the air, we've got the atmosphere. But luckily the refractive index of air is very nearly 1 because the speed of light in air is very nearly the same as the speed of light in a vacuum. So we can use the approximation that the refractive index, N, is the ratio of the speed of light in air to the speed of light in our more dense medium. So the same relationship, but we can use the approximation that it's the speed of light in air on the top and the speed of light in the more dense medium on the bottom. It's always the less dense material that's on the top, regardless of which way the light is travelling. So V1 is always the speed of light in air. Now, because the light slows down and the waves bunch up, then the wavelength in a vacuum, or the wavelength in air, is longer than the wavelength in the material. When the light goes into the material, into the optical substance, then the waves bunch up so the wavelength gets shorter. And we can extend our relationship so that it looks like this. The ratio of the wavelength in air divided by the wavelength in glass is also equal to the refractive index. So there's our wavelength in air, wavelength in glass, or the wavelength in the more dense medium, and the wavelength of the light in air divided by the wavelength in the more dense medium also gives you the refractive index, gives you that number. It's a ratio, doesn't have any units. And sometimes instead of the numbers 1 and 2, you'll see subscripts for the substances, A for air, G for glass. Now, what are the refractive indexes or indices of selected substances? Well, you maybe noticed a table on your data sheet that's got refractive indices on it. There it's there. And there's some common substances. And what you'll notice is refractive index is always a number greater than 1, but it's never really any greater. Well, diamond has got the greatest refractive index that you'll probably see, 2.4. So they are numbers that are very similar, between about 1 and, well, I don't think you'll see anything over 2. But what happens if a solid and a liquid have the same refractive index and you put the solid in the liquid? Well, there's a little, there's a wee hyperlink there if you want to watch it. Go to the actual PowerPoint and watch that. Right, time for a wee example. If we have a red light, so over here I have a red laser and it's shining through a jelly. The jelly has got a refractive index of 1.35 and the wavelength of the light is 658 nanometers. And here's a question. Calculate the speed of light in the jelly. Well, it'll slow down. What's the wavelength of the red light in the jelly? Well, it'll be less than 658. And calculate the frequency of the light in air and jelly. So let's try this. So part A, the speed of light in the jelly. Remember, the light is going to slow down when it goes from air into the jelly. So we use our relationship. N equals V1 over V2. V1 is the speed of light in air. That's 3 times 10 to the 8. And it's V2 that we're looking for, the speed of light in the jelly. So we rearrange that relationship. And it's V2, just swap the V2 in the N. So V2 equals V1 over N. I know that V1 is 3 times 10 to the 8. And N is the refractive index of the jelly, which is 1.35. Oops, I put 1.25 there. Hopefully I'll do this right on my calculator. 3 times 10 to the 8 divided by 1.35 is 2.22 times 10 to the 8. Remember, the speed of light should be slower, which it is. Part B, what's the wavelength of the red light in the jelly? Well, we can use the same relationship. So N is equal to the wavelength of the light in air over the wavelength of light in the jelly. And again, we're rearranging this to get the wavelength of light in the jelly. So it's going to be the wavelength of light in the air divided by the refractive index. Remember, these waves are going to bunch up, so they're going to get shorter in wavelength. So 658 divided by 1.35 gives us 487 nanometers. Now, I didn't put the nanometers into my calculator. I didn't put the 658 times 10 to the minus 9 into my calculator. I'm just going to do 658 divided by 1.35 as long as I remember that that is in nanometers. Part C is calculate the frequency of the light in air and in jelly. Well, if we want the frequency of light in air, it's the speed of light in air over the wavelength in air. Remember, the wavelength in air was 658 times 10 to the minus 9 nanometers. And if I do that on my calculator, I get 4.6 times 10 to the 14 hertz. Now that's the frequency in air, 3 times 10 to the 8 divided by 658. The speed of light in air divided by the wavelength in air. If we do the same calculation, but we use the speed of light in the jelly and the wavelength in the jelly, remember it's slowed down and they're bunched up. So it's 2.22 times 10 to the 8 divided by 487 times 10 to the minus 9. And if I do that in my calculator, I get 4.6 times 10 to the 14. So it doesn't matter if you do it in air or in the jelly, the frequency stays the same. The frequency is always unchanged. The number of waves per second always stays the same. Okay, Snell's law. You should remember from National 5 that if light enters a more dense substance, for example water or glass, at an angle to the normal, then the direction of the light changes when it enters the glass. Now, a Dutch astronomer called Willebrord Snellius in the early 1600s discovered the relationship between the angle in the air and the angle in the glass, and it's known as Snell's law. So there's a sort of diagram you would have seen at National 5, where you've got a ray of light in air and it's entering the glass, or it's entering, I don't know what substance 2 is, it might be water or it might be glass, but it's entering the glass at an angle to the normal, so there's an angle of incidence, and when it enters the glass it bends towards the normal, and there's an angle of refraction that is smaller than the angle of incidence. And Snell discovered the mathematical relationship between these two angles, and we're going to do a wee demo to see if we can find out that relationship as well. Right, okay everybody, today we're having a wee look at refraction, and in particular Snell's law of refraction. Now, you should have looked at light and the way that it behaves when it goes through various shapes of glass, maybe in first or second year, but we're going to have a look at that in a bit more detail at higher physics, and to see if there is a relationship between the light and the air and the material that it passes through. So if we shine a ray of light just now, we've got a rectangular block there, and if the light hits the glass block at this side here, if it hits it at 90 degrees, it passes straight through as normal. And so what we usually do, I'm going to draw around that block, and I'm going to put a dotted line on at right angles to the block. Give me a wee second. So if I draw around that block, and if I then take the block off and draw a normal, now normal is just a dotted line at right angles to the surface. Now, I'm going to make sure that it is 90 degrees. I'm going to get my protractor. Now, protractors may be something you haven't used for a long time, but a protractor is used for measuring angles. So I'm going to see if I can very carefully put a dotted line at right angles to the glass. A dotted line at right angles to a surface is called a normal. And if we shine light along that normal and we put a glass block on it, then the light continues through the glass in a straight line and carries on as normal. We don't observe any change in the direction that the light's travelling. But what happens if we shine that light in at an angle? Let's set this up. I've taken my block off the page, I've put my protractor on so that 0 on the protractor is at the normal, and I'm going to measure 20, 40, 60, 80 degrees from the normal, and then I'm going to draw a straight line. So this line here is going to represent my ray of light that is hitting the glass block at an angle of 20 degrees from the normal. This one here is going to represent 40 degrees. Now, if I shine a ray of light along these paths, they are hitting the block at that point there, and the normal's at 90 degrees to that. So that's 40 degrees, that's 60 degrees, and that's 80 degrees. Now, I've just done it pretty roughly, but that's the idea. If that's 20, that's 40, that's 60, and that's 80. What happens to the light if we shine that light along those rays and we put the glass block on? Now remember, if you shine the light directly along the normal, it continues as normal, goes straight through. But what happens if we go in at 20 degrees? Well, at 20 degrees, you may have done this lower down in school, second year or first year, when the light goes from air into glass, it bends towards the normal. There's a little bit of reflection as well, we're going to ignore that. But when the light goes into the glass, it bends towards the normal, and when it exits the glass again, it bends away from the normal. You might not be able to see it too well at my 20-degree angle. You might see it better when I put the light in at 40 degrees. At 40 degrees, if I get right overhead, you should see that the path of the light is bent towards the normal in the glass and bends away from the normal when it exits the glass again. I'm going to trace the path of the rays as they go through that block. There's me back at my 20 degrees again. And what I'm going to do is I'm going to put a couple of marks where the ray comes back out, and then I'm going to join all those lines up with my ruler. So that's where the ray came back out. I join that up and then join that up. And I'm going to put a normal here as well, where the ray exited the glass. I should really use my protractor for this. Now, here's the key point. Here's the bit we want to investigate here. If the angle it went in was 20 degrees, what's the angle to the normal in the glass? Well, I can use my protractor and measure that angle. If I very carefully put that on there, my refracted ray, the ray in the glass, is about 13 degrees. 13 degrees. Here, that angle there is about 13. So for each of these angles, 20, 40, 60 and 80, I can produce a table. And that table will give me the angle of incidence. In physics we usually use a little symbol, theta, for angle. So the angle it goes in, the angle it's refracted at, and we'll see what they look like for each of my rays. So I'm going to repeat it at 40, 60, 80. So I'm going to put my block back on. I'm going to get my 40 degree ray. Shine it along at 40, and there's my ray when it exits again. So a couple of marks on there. Take the block off, take that out, and if I join these up, then that is the path of my 40 degree ray. Now it's starting to get a little bit complicated looking here. Put another normal in. Hey? That's my 40 degree ray. Let's put two arrows on it. This is my 40 degree ray. This is my 40 degree ray. I wonder what that angle is. That big angle. Get my protractor again and measure that angle. And so measuring that as carefully as I can, it's about 25 degrees. 25, maybe 26. Let's go with 25. So when my ray went in at 20 degrees, it was refracted at 13. When it went in at 40 degrees, it was refracted at 25. It's going to get a wee bit cluttered here. So I'm going to get another bit of paper and do the same again, but for 60 and 80 degrees. Right, I've rejoined round my block, and we're only going to do the 60 degree one. Well, we could try 80 as well. Right, so what I did very carefully was I drew round the block, I drew a normal at right angles to the side of the block, and then I have measured 60 degrees from the normal, put the 0 at the normal, 60 degrees, and I'm going to shine my ray of light along there, and I'm going to place the block on the sheet of paper and see what the light is refracted at. So, put the block on. Now again we're getting a wee bit of reflection from on this side of the block, we're going to ignore that, but the refracted ray as it goes through the glass, if I put a little dot there, a little dot there, I can trace the path of that ray through the glass. So, let me just move it on the road. Here's my refracted ray. And join it up here. And the question is, what is this angle? It's smaller than 60 degrees. If I measure it with my protractor, then I get about 35 degrees. Okay, that's 30, that's 40, halfway, 35 degrees. If I try it at 80 degrees, just put my protractor on. There's 80 there. Yeah? Let me just see what happens. If I try doing this at 80 degrees, it's just going to skirt the side of the glass. And it's impossible to see a refracted ray, so it's pretty much all getting reflected now from the side here. And we're not getting a lot of refracted rays, so I'm going to ignore the 80 degree one. But we have results for 20 degrees it was refracted at 13, at 40 degrees it was refracted at 25, and at 60 degrees it was refracted at 35. That is the angle in air. That's the angle in glass. And the big question is, what is the relationship? Is there some mathematical relationship between the angle in air and the angle in glass? And has it got something to do with the light? Has it got something to do with the glass? Let's think about that. Right, here's our Snell's law experiment. Remember, the ray of light was passing through the glass like this, and it was entering the glass at an angle, and we're going to call that angle the angle of incidence, theta I. You could also call it the angle in air. And the angle that it was in the glass measured to the normal, we're going to call the angle of refraction. It could also be called the angle in the glass, theta G. And we shone our rays of light in at 20, 40 and 60 degrees, and we measured the refracted rays, and at 20 degrees our refracted ray was 13, at 40 it was 25, and at 60 degrees it was 35. Now what's the relationship between them? It's not as simple as if you double the angle in air, you double the angle in glass. So it's not as straightforward as that. And Snell messed about really with these angles, and eventually he came up with a relationship. He discovered that if you take the sine of the angle in air and the sine of the angle in glass, and you divide sine of the angle in air divided by the sine of the angle in the glass, then you get a constant number. So let's do that. Let's put another column in the table there. Let's do the sine of the angle in air divided by the sine of the angle in glass. And if I do that in my calculator, then sine 20 divided by sine 13 is 1.52. And if I do the other ones as well, sine 40 over sine 25 is 1.52. And sine 60 over sine 35 is 1.52. The sine of the angle in air divided by the sine of the angle in glass is a constant, and that constant is the refractive index of the material. And remember, we use the symbol N for refractive index, so we can now write the relationship like this. The refractive index is the sine of the angle of incidence divided by the sine of the angle of refraction, or N equals the sine of the angle in air over the sine of the angle in glass. And that relationship is on your relationship sheet. Now, in fact, that relationship can be extended to include the speed and the wavelength and the angles and we can write it like this. The refractive index is the ratio of the speed of light in air to the speed of light in glass. The refractive index is the ratio of the wavelength in air to the wavelength in glass, and the refractive index is the ratio of the sine of the angle in air to the sine of the angle in glass. And if that's the case, we can write all this in one big relationship. N equals speed of light in air over the speed of light in glass, which is also equal to lambda in air over lambda in glass, which is also equal to the sine of the angle in air over the sine of the angle in glass. Remember, these subscripts can be A's and G's or 1's and 2's or whatever your substances are, but that relationship is on your relationship sheet, and it can be used to solve a variety of questions about refractive index. Right, a couple of points to note before we go. Remember, this was the path of a ray as it went from air into glass and back out the other side. That was the angle of incidence, or the angle in air. That was the angle of refraction, or the angle in glass. Now, if you look closely here, because it's a rectangular block, that angle there is the same as that angle there. It's a Z angle. So that angle in glass is the same as that angle in glass. So therefore, when we come out the other side, that angle in air is the same as that angle in air. So watch out for what we call Z angles. I'm sure you did Z angles down with your maths in first year. And it doesn't actually matter if the ray of light is going from left to right through the glass. It could go in the opposite direction and follow exactly the same path. So in a rectangular block, the ray exits the block parallel to the incident ray. Don't know if I quite showed that perfectly, but they'll be parallel. Use Z angles in a rectangular block, and as it enters the glass block, remember, it bends towards the normal, it slows down, and the wavelength decreases. So as it exits the glass, it's going to bend away from the normal, it's going to speed up, and the wavelength will increase. And when we say speed up, we really mean it returns to the speed of light in air, and the wavelength returns to the wavelength in air. Now, for more complex shapes like prisms and lenses, you will have to do a bit of geometry. The same process applies, but you might have to use a wee bit of your maths knowledge. Okay, that's us.